Hello, everyone. Welcome to the session A9 on traceability in day 2 of ICSI. Our first speaker today is Monifa Alenazzi. She'll be talking about a novel approach to tracing safety requirements and state-based design models. Please post all your questions that you have during the presentation on the Slido on the left-hand corner of your screen. Thank you.
Hello, everyone. Excellent. Thank you for joining this presentation on our paper titled A Novel Approach to Tracing Safety Requirements and State-Based Design Models. This is Monifa Alenazzi from University of Cincinnati. This work is a collaboration with my advisor, Professor Nanyu, and our industry partner, Juha Savolainen from Danfoss Drives. Our paper overcomes the problem of the low precision challenge that faces automated requirements traceability. Traceability, which refers to the ability to follow the life of requirements, has long been recognized as an important component in building safety-critical systems. Therefore, traceability plays an essential role in assuring that software and systems are safe to use. With the use of model-driven engineering being on the rise, state-based models become larger and more complex. This represents a significant challenge for inspectors where they have to browse through the models and manually analyze a large number of links between safety requirements and design models. Therefore, researchers have proposed many techniques like model slicing and NLP to automatically establish and evolve trace links. However, automated requirement traceability still faces the low precision challenge because of a large number of false positives being returned and mingled with the true links. State-of-the-art approaches show a precision of only 29.4%. To overcome this challenge, in this study, we present a mutation-driven method built on the novel idea of generating many false positives or many mutants from a state-based model, and then leverage model checking to check whether the safety requirement is met in these mutants in order to identify the candidate trace links. Before describing our approach, we define a traceability information model, TIM, that underlies our work. TIM explicitly records what artifacts are important and what others are not under the current traceability consideration. As Mader and his colleagues states, defining a traceability information model early in the project is key to the development of safety-critical systems. This figure presents our TIM. While the safety property presents the tracing source, the tracing target is a state machine diagram. I would like to mention here that this TIM delineates the focuses of our work. In other words, it's beyond our current scope to trace a single safety property over multiple SMDs or different type of SysML modeling like internal block diagram or activity diagram. I will now present in brief the steps of our approach. At first, we export the SMD under test into an XML file, and then we convert it to an event log. The safety property P is transformed into LTL formula. After proper configuration, we perform model checking within a process mining, especially its LTL model checker. If failed, we then have to refine either the property or the design model. The main reason behind this step is that if the model checker fails, then the requirement is not implemented, so no tracing should be performed. If passed, then this leads to the first step of our approach, which is creating mutants of the SMD. These mutants are based on the mistakes commonly made in SMD modeling. We surveyed the literature to identify these mistakes and identified 15 mutation operators. We developed Python script to modify the XML file, the original one, by leveraging some of these identified operators. After generating all these mutants, we converted to an event log. We leverage LTL checker with process mining. Our model mutants are good fit to process mining in that the flexibility of each mutant is restricted to only a single change over the original SMD. After performing model checking, we are interested in obtaining two models, one that underlying all the killed mutants and the other one for all the survived ones. We said that a mutant is killed if its model checking fails, otherwise it survived. These mutants are in form of matrices. Recognizing the killed versus the survived mutants allows our final step to identify the candidate trace link. This figure here represents our algorithm. To maintain a high recall, we initializes L with all the states of M. We then check the pair of states that only having positive correlation in the killed mutants. For each of the selected pair in the killed mutants, we mark both states with remove if the two conditions in line number 3 are met. That is, the correlation of score of the selected pair is greater than a threshold K, and the difference between the correlation score of that selected pair in the killed and in the survived mutants is greater than 1. Having made the marks on all the examined states, we remove from L these states received marks and only remove marks. The candidate trace lengths by our algorithm lead to a recall of 100% and 75% of precision using the running example in our paper. To evaluate our approach, we set the following questions. How accurate is our proposed mutation-driven approach, a traceability approach? While our main goal is to improve precision, we also don't want to hurt recall. Thus, our measures also include F1, which is the harmonic mean of recall and precision. The second research question is how to best operate our approach in a practical setting. Since the threshold K is key to identify removable states, we are interested to discover what optimal value that could improve the precision. For accuracy comparison, we use backward slicing and forward slicing algorithm as our baseline. Our experiments are carried out in the context of two subject systems, mainly the adaptive cruise control and power system, using 26 models and 27 requirements. The answer to the first research question is presented here in this table, where the recall, precision, and F1 values are reported. As you could see in the result, using model checking to dynamically verify the SMD and its mutants, improve the average precision by over 10% without hurting the recall at 100%. Our approach doesn't rely on structural dependency like backward slicing, and therefore doesn't face the challenge of which direction to slice and when to stop slicing. To answer the second research question, we calibrate threshold K and measure how it impacts precision. The results suggest the threshold K range of 0.6 to 0.8 further improve precision to 75 for ACC and 73 for the power system. This figure, as recalled, is maintained at 100% throughout the calibration. This figure plots only the impact on precision. To conclude, a mutation-driven approach to tracing safety requirements and SMD modeling is proposed, and the results show precision improvements. The novelty of our work lies in our creation of many mutants, leading to new way of establishing traceability links. In the future, we would like to expand our TIM to handle first more complex requirements and include other diagrams like activity diagrams and a block definition diagram. We also would like to improve the usability of model slices in a form of visualization. Thank you for listening, and I'm ready to take your question.
Thank you very much, Monifa. I think we have one question here from an anonymous colleague. Our collaborators' projects have millions of artifacts per project. Will this approach scale?
There are many artifacts. Our paper focuses only in the tracing between the safety requirement and the design models. So it doesn't include any source code.
Okay. And you said that you will be extending for the type of requirements. Which other type of requirements do you have in mind as the next step?
There are some safety requirements that can't be translated to LTL formula. So we would like to know how could we include those in our approach.
Okay, thank you very much. Thank you for the nice presentation.
Thank you.
And I think we can move to our next presenter that will be talking about establishing multi-level test-to-code traceability links. This work has been done by Robert White, James Crinkle, and Raymond Tan from University College London, and Robert White will be giving us the presentation.
Here we go. Right. Hello, everyone, and welcome to this talk. So the work is about establishing multi-level test-to-code traceability links, and it was performed by myself, a PhD student at the Crest Centre in University College London. That's Robert White. Jens Krinker is my supervisor, and Raymond Tan is a postgraduate student there. Okay. So essentially the purpose of the work is to establish a technique for building test-to-code traceability links. So we're looking to build links that map test artifacts to their tested artifacts. So at the class level, we're looking for the test classes to link to the tested classes and individual tests to link to tested methods at the method level. So why do we want to maintain these kind of links? Well, there are three primary benefits to doing so. So firstly, we want to keep tests in sync with code. So whenever we update code, we want to also update their retrospective tests to make sure that everything is staying in sync. And by doing this, we should get fewer test failures and fewer missed faults. They're also useful for maintaining architectural consistency. So for example, if the architecture of your project demands a one-to-one mapping between test classes and tested classes, you can use these traceability links to ensure that that architecture stays consistent as the project evolves. These kind of links can also be used for other things, such as discovering tests for use in recommender systems, or for building corpuses of training data for machine learning models that can be applied in a whole range of scenarios. So these kind of links can be really beneficial for a standard software engineering process, but also for research tools or other types of things. However, manually maintaining these links is time-consuming and error-prone. And therefore, where it is attempted to be done manually, it's usually only done at the class level, very rarely at the method level. So because of that, ideally, we want to find some kind of automated technique for building and maintaining these linked databases. So when we look at previous work, there have been a few different types of techniques that have been tried to solve this problem. And these are the four main ones. Now, each of these techniques does have its own benefits, but they all have very significant weaknesses. So if we look at the simple call-based techniques, we find that they do a lot of over-approximation. So this is simply where you draw a link between a test and a function for every function that the test executes. And in that case, we would see things like getters and setters and utility functions being linked when really they're not actually the tested function. For naming conventions, we see that where a project does follow the naming conventions, they can be very high precision. However, they are very low recall where a project doesn't follow a naming convention or where tests test multiple functions. For last call before assert, the problem is that the assumption does not always hold. So the last executed function is not always the tested function. You can see this where it might be a getter or it might be a function that establishes an oracle. And for the information retrieval techniques, there's an inherent weakness there in that they treat code in the same way as though it's natural language, which we know they're not the same thing because code has a bimodality. It's not just the lexical information, it has semantic information, and treating it the same as natural language is quite weak in a lot of ways. So all of these techniques have problems. So what we've done is develop an approach and an implementation that we're calling TC Tracer, which is designed to overcome all of the individual weaknesses of the existing techniques. And there are three main ways in which we do this. Firstly, we utilize an ensemble of existing and new techniques, which I'll show in a minute. We operate at both the method and the class level, so we're establishing both types of traceability links, and we're the first system to tackle both levels at once. And then because of that, we can use multi-level information to improve our effectiveness at each individual level through augmenting, which I'll show. So our technique ensemble is the set of techniques that we use, and they're split into two groups. So we've got naming-based and call-based. For the naming-based techniques, we've selected the traditional naming conventions, like I mentioned earlier, in which case we link a test and a function if the names match exactly after the word test has been removed from the test name. However, given the weaknesses that I previously mentioned, we've also developed a variant of that we're calling NCC, in which the test only needs to contain the name of the function. It doesn't have to match exactly. And that allows us to match in instances where a test tests multiple functions, this allows us to do that. We then have two techniques that are based on longest common subsequence. And the first is kind of an extension of the traditional naming conventions, and that it's a real valued score rather than a binary score. But here we maximize the real value score when the test name and the function name match exactly. That's why it's an extension of traditional naming conventions. The second LCS technique is an extension in the same way of the NCC technique. So essentially what these are is they're taking the same concepts as the first two techniques, but they're applying a real valued score rather than a binary score. We then also have a technique that's based off of the Levenshtein distance, and we basically scale the Levenshtein distance by the length of the longest string, which again is a real valued score. So those are the naming-based techniques. For the call-based techniques, we use LCBA, which I mentioned earlier, and we also have a technique based on term frequency, inverse document frequency from information retrieval. So if you're familiar with that technique, essentially we do the same thing, it's the same principle. However, we take the role of the terms and we use functions instead, and the role of the documents, and we use tests instead. And we apply it in the same way. In a similar vein, we also have a technique that's based off of tarantula, statistical fault localization. And in that case, we take the test under consideration, which is the test that we're trying to build the links for, and we assume that that test fails and that all other tests pass. We then use tarantula to find the relevant functions and draw links between them. So that's the technique. So, but if we look at the overall TC Tracer approach, essentially it breaks down into method level and class level. So if we start on the method level here, we take the tests and the functions, we apply all of our techniques, which I just showed. We then also compute a combined score of all of the techniques, which is simply an average of all of the individual scores. And those scores make up our method level scores. We then use those, we take those scores, apply thresholds to them to generate our link predictions at the method level. Then if we move over to the class level, we see we do the exact same thing to create the class level scores. So so we now have the predictions for each level using just that information. Next, we move on to the multi-level information. And here what we do, the first thing we do is take the method level scores and we elevate them to the class level. So essentially we're using the method level information to try and make predictions at the class level. That gives us those scores, which we then make those predictions. Then back over at the method level, we take the class level scores and the method level scores and combine them to create the augmented method level scores, and we again produce predictions from that. So we end up with 4 sets of predictions. Okay, now for the ground truth, we have 3 projects at the method level, 4 projects at the class level. And we have 138 manually generated Oracle links at the method level. And that data set is available at that link at the bottom if anyone would like to use it. At the class level, we have the vast majority of the links are provided by developers. So we did actually find that in these projects, the developers had manually maintained some class level links. So we use those as our ground truth. For the evaluation measures, we have the standard types of measures. Most importantly, we have mean average precision and area under the curve. MAP is really important for establishing ranking performance, and AUC is important because it's independent of the thresholds. So for research question 1, we're looking at how do the techniques perform for generating method level links using just method level information. And we see here that overall, the combined technique is the most desirable because it has the highest MAP and AUC. So what that shows us is that it's good at ranking predictions and it's consistent when changing thresholds. And it could also benefit from more optimized thresholds, which is nice. For RQ2, we're looking at how we perform at the class level using just the class level scores. And the overall picture that we see is pretty similar to the method level in terms of how the techniques perform. But overall, the scores are higher because it is an easier task. So moving on to RQ3, now we're looking at how successful are we at creating class level links using method level information. So this is the elevated method level information. And we see that overall, the results here are not as good as RQ2. So what that shows us is that in this instance, it's better to just use the class level information from predicting these links. However, when we look at RQ4, this is where we use the multi-level information for method level predictions. And we see that overall augmentation does improve the results. So in this case, it's better to use the multi-level information. Okay, so that was TC Tracer, approach and implementation for establishing tester code traceability links. We're the first system to establish links at both the method and the class level, and we improve on the state of the art by using a combination of new and existing techniques with the multi-level information. And if you would like to use the code or the artifacts, they're available at that link. Thank you very much.
Thank you, Robert. I think we have some questions here and time for a couple of questions. There's a question from Jane. In industrial practice, the greater challenge is in maintaining and evolving, not creating links. How would you maintain such fine-grained links?
Yes, so we can easily integrate into continuous integration systems. So we have an agent that plugs into JUnit. And then, so all that we do is we attach to JUnit via a Java agent, which runs at the time, obviously, that the test are executed. And then that produces the relevant data that we need to then actually run onto the tool. So all that you would do is just add an extra step into your CI process that executes the tool, and you can refresh the links every time the CI process runs. And it's fast as well.
Okay, think we. Thank you.
Okay.
We have a, oh, there was another question that, yes, there is another question here from Jane as well. I think it's the time for the last one. What would the task of evaluating and vetting links look like at the method level to address the precision problem?
Sorry, could you repeat the question?
What would the task of evaluating and vetting links look like at the method level to address the precision problem?
So for evaluating and vetting links, yes. So we do that. So where we built the ground truth, for example, we just did that on a manual judgment, basically. So we had a panel of 3 judges, each look at our random selection of links and, random selection of tests, and just make a manual assessment on what the linked function should be. And then where there were differences, we had a discussion about that. But yeah, essentially it was just a manual judgment.
Okay. Okay, thank you. And there is opportunity to find the speakers of the session later on and address some of the questions. I just want to remind all the participants to send their questions in Slido during the presentation, because we have a very restricted time for questions just after the presentation. Our next speaker is of a near paper, Synthesis of Assurance Cases for Software Certification. And our speaker is El-Sung Kang from Carnegie Mellon University.
Can you see my screen? Okay. Thanks everyone for coming. My name is El-Sung Kang, and I'm going to tell you briefly about some of our ongoing work on software certification. And this is joint work with Hamid Baderi and Niloufar Mansour at the University of Nebraska-Lincoln. Certification is the process of demonstrating to a third party that your system is sufficiently safe, secure, and functional before it can be deployed into the market. And depending on the domain that you're working in, there's been a different range of standards that's been developed typically by government agencies to ensure that your system satisfies a certain level of quality. So certification is an active area of research right now. And one of the major approaches to certification is what are called assurance cases. So assurance case is an explicit argument designed to demonstrate that your system satisfies a set of certification requirements along with evidence to back up the claim. And so assurance case typically consists of three major components. The first, the top level claim, which corresponds to a particular requirement that you're trying to demonstrate, and the argument itself, which consists of a set of subclaims that are together should logically imply the top level claim. And finally, you have a set of evidence that are generated by the developer. And the evidence can range from testing, program analysis, verification, to inspection, and the opinions of a domain expert. So there are a number of challenges that to overcome before assurance cases can be used in more widespread in practice. And one of the major challenges is that the arguments in assurance cases are typically written informally using a natural language. And the relationship between a pair of claims or a claim and the evidence can be unclear and ambiguous at times. And this also makes it hard for third-party auditors to check or validate the soundness of the argument. Second, it just takes a lot of effort to generate the evidence that are needed to support an assurance case. And what makes this worse is that if you construct the assurance case manually, then every time the system changes, which is quite often nowadays in modern software systems, that you may have to rebuild the entire case from scratch and also regenerate all of the evidence. So in this paper, our conjecture is that a lot of tasks that are involved in the construction of assurance case and as well as generation of evidence can actually be automated using the techniques that we have developed in software engineering. In particular, our agenda is to combine two different kinds of analysis, one at the level of architecture to rigorously drive subclaims from the top level claim, and then at the level of implementation to automatically synthesize analyzers that are designed to generate evidence needed for the assurance case. So I'm just going to go through each one of these very briefly and then tell you about what they are. So the first sort of part of our agenda is to develop a technique called what we call architectural-driven property decomposition, which is going to take an architectural description of a system as well as some certification requirement that you're trying to establish, and then automatically generate a set of subclaims that correspond to the specifications on the behavioral components. And by construction, these subclaims should imply the top-level claim. The second part of our agenda is to develop a technique called analysis synthesis, which is going to, given a particular component spec, search through a set of library of existing analysis and try to synthesize a specialized analyzer that's going to generate the evidence exactly needed to discharge this spec. There's a lot more details in the paper, but just the one takeaway from this talk is that certification is becoming much more important nowadays, and there's a lot of potential to improve the state of the art by automating many of the tasks that are involved. And we're actually in particular very excited about combining different kind of analysis at the level of architecture as the implementation. Thank you, and I'll be happy to take any questions.
Thank you very much. I think we have one question from Jane that Nancy Levinson in her keynote address claimed that assurance cases are the wrong approach for achieving safety. Can you comment on this with respect to your work, please?
A great question. And I have to say, this is one place where I disagree with Nancy, even though I respect a lot of Nancy's work. And I do believe that assurance case serves a very important purpose as sort of demonstrating to third-party auditors that the system actually satisfies a set of safety requirements. And I do believe that this is going to play an important role in coming years. So my answer is, I believe it's important, although Nancy might believe it's not important.
Thank you. Thank you very much. I think we need to move for our next question. And again, the presenters will be available for more questions later on in the lobby. Our next talk is a demo of Time Tracer, a tool for back-in-time traceability replaying from Felix Kepling and Christopher May, and several authors also from Johannes Kepler University.
Welcome to the demo for time tracing, back-in-time traceability replaying. We use chronology as an example where we have a lot of issues that represent requirements, issues, safety cases, and so on that have a lot of changes that change in different times and different phases of the project, and that have a lot of trace links that also, again, change frequently across time. These we want to track to see what state was the project in at a particular time. To this end, we store these artifacts in a graph database where each of these issues and each of these artifacts becomes a node, and we track which relations are between these, so which traces are between these nodes. Additionally, we store all the changes in these database as well. The Java API itself provides then ability to forward change by change in either direction or forward and backward to a particular time as desired. So we have, for example, forward where we just apply the next time change, or we can also go back in changes where we kind of apply first the newest change and then apply all the changes then. For our demo purpose, we integrated with a quality constraint checker that allows us to check the state and the traces at a particular time. For that, we have a command line interface and we load the session. So in this case, we load around 10,000 changes from 1,000 issues, set it to the earlier state, insert them into our quality constraint checker, which means it analyzes those JIRA issues now that we add. In this case, there's some requirements. Then we check these constraints. And then we look in our tool, in this case, an add-on, where we have for each issue, for each process, basically the trace checks and the quality checks. And here we see that there was just one step and 2 constraints have been checked and both are not fulfilled yet. So we have checked this for every single issue. Now we forward this, for example, to a recent time. Again, we do this for the whole database. It's really quick to apply those changes, as you can see here. And again, we just select these artifacts. It's because due to work in progress, it's not quite done, quite convenient yet. And here now you see we load the new versions. So the more recent versions, we see there are more steps per process, and there were also additional traces now, additional checks that were done now. Thank you.
Thank you very much. Again, Felix will be available later on for questions. I would like to introduce our next talk, that is lack of adoption of units of measurement libraries, survey and anecdotes. And our speaker today is Steve McKeever from Uppsala University.
Hi, so I'm presenting lack of adoption of units of measurement by Omar and myself. So what we're talking about here is adding units of measurements to conventional programming languages through the medium of libraries in order to get type-safe manner to avoid the problems of the Mars Climate Orbiter that we've all heard of so often. In a previous study, we classified unit of measurement libraries found on open source repositories. And even a simple search found over 65,000 projects, of which 3,700 were actively developed. And then we filtered further and we got down to 82 that represented the most prominent, covering many of the usual programming languages. So unit of measurement libraries exist for all programming languages, basically. And we postulated there that there was too much diversity, lack of code sharing, and duplicated efforts were discouraging adoption. And then I went further and I looked into some of these most prominent libraries and realized that they were all doing the same thing. They were all implementing a version of the quantity pattern. They were not doing a large class hierarchy. What they were doing was using this very clever normal form, but it didn't answer the question as to why there was no de facto standard or a huge evidence of usage of these libraries. So this is where I was interested in getting a master's student to work on this. And he performed this study where he took some interviews, ran a survey, and then looked for common themes, characteristics, and then propose some recommendations. So I'm going to go through this, these factors that emerged. Our study involved 4 interviews, 1 physicist at Uppsala, 2 Java unit library developers, and 1 functional programmer, along with a survey that had 91 respondents, and they were mostly developers. And from there, we used qualitative coding and we extracted factors. Each factor is a theme, and a theme was only deemed significant. It was repeated as a concern between different interview subjects and questionnaire respondents. Now, I've grouped the themes into 3 for the purpose of this talk. Basically, issues that stop people from even using unit of measurement libraries, issues that, if they want to use them, slow them down, and external factors. I'd advise you to look at the paper to find all the quotes. We have lots of lovely little quotes that come back in the conclusion. Okay, so one of the main reoccurring phenomena here was that people just don't know there are unit of measurement libraries out there. So even though there's over 65,000 on GitHub and SourceForge and all the rest of it, people don't know that. And a lack of concern was also a reason why people don't use them. They just didn't feel they were necessary, even if they're solving safety critical problems. And a large number of non-adopters of unit of measurement libraries felt that they didn't really provide any gain. It's known that a variable needs to annotate a variable with a unit takes on average 2 minutes, and lots of mistakes are made. So there's this general feeling that you can cause more problems than you solve by using unit of measurement libraries. Again, this is the kind of thing people would say about any libraries, but it cropped up here as well. And also the fact that they're not as intuitive as you might expect. It's a very simple problem. We're aware of it from school, but once you start looking at these libraries themselves, they become a bit quirky, a bit harder to see the benefit of using them. But I think one of the main reasons here is about tradition. If your research group doesn't use these libraries, why would you begin using them in the first place? So if you're doing heart modeling, all that matters is the results of your heart simulations, not the fact that your code is robust. What matters is when you start linking in with a lung heart model, heart and lung model, and you might have the wrong size of veins and arteries. But that's not your concern of the research group themselves. And also that the not invented here syndrome was another reason for not even beginning to use libraries. Moving on to technical internal factors was the lack of obvious return on investment. So even if you used the libraries, it wasn't always clear why you would need to do them, because these errors only come up once in a while, even if they can be fatal when they come up. There's also a whole host of efficiency, speed, and such reasons here, is that many people use unit of measurement libraries thinking that they're a compile time construct, that you want them to use the type checker to try and stop you adding a meter to a mile and something like that. When in actual fact, there's a lot of people who want runtime checking. So they want your software, their software, to be able to take in a meter, a kilometer, a mile, and just work seamlessly, do all the conversions correctly, and so on. So with that in mind, the fact that you have this way of adding on units to an object-oriented language is going to cause you some efficiency concerns unless it's completely handled at compile time. So a lot of these libraries give a runtime hit, and it's unacceptable for large-scale scientific computations. Moreover, because they don't work at the compile phase, they're working either at the type checking phase, they don't do any great symbolic evaluation. So their conversions are not optimal. So you end up having lots of round-off errors. And that also causes problems. People who are doing scientific computing need correctness, or least amount of errors as possible. And strangely enough, one of the other reasons we saw was that some of these systems, even if they're very mature, struggle with complex derived units. So if you divide a force by kilogram, it's not obvious that you've got acceleration in some of these cases. They're not able to deal with that very well. But I think one of the main reasons that is a problem, and it's not spoken about directly, but it came out of a lot of our comments, was the cost of porting existing code. There is no point in having units in your programming language if your database does not support them. You have to think about your ecosphere, and that's not a concern for most of these developers. And alongside there, you have the problem that they're hard to use. So not only is it an ecosphere problem, but actually gaining traction with your team may be very difficult. So there were quite a few comments about people preferring to write unit tests. So if we summarize all the factors, what we have is the following obvious conclusions: that people want simplicity in their unit of measurement libraries. So that means you might want to hide your generic style object-oriented code using syntactic sugar or through support of an IDE. You want them to be idiomatic with the programming language, you want meaningful error messages, and you want flexible types. You want to be able to deal with a double and a float of a particular unit. This is not always the case. So you end up having to use one or the other, and that's maybe not the right way you want to program. So to summarize even further, you could just say that unit of measurement types need to be as easy to use as arithmetic types. And that's no surprise, and it's not as if people haven't been trying to do that. In a sense, they've failed. And I think they've failed for the fact that it's not as easy as one hopes, but also for two big reasons that have come up from these comments, two technical reasons. One is the compile time runtime dilemma. And most of these unit of measurement libraries are compile time, but they also have a runtime hit. And people want one or the other. They don't want this mixture. But more importantly, you've got the problem of integrating with the ecosphere, and you have alternatives. So we have the four alternatives. You can choose to use unit of measurement libraries. You can choose maybe a more lightweight approach, not as secure, but one that just involves annotating as much as you know, and annotating especially at the component level. So you can annotate the group working on miles and annotate the group, sorry, not that the group can work in the imperial system and another group can work in the metric system, but only when they come together do you make sure they're talking the same language, and that would have solved the Mars Climate Orbiter problem, for example. Then you have languages like F#, which do symbolic and a very good equational computation of units at compile time, very secure, very flexible, and you also have unit testing. So I think combined, some of these technical problems and the fact that you have competing approaches explains why there's a lack of adoption of unit of measurement libraries. And thank you very much for listening. Any questions?
Yes. Thank you very much, Steve. We have one question from an anonymous colleague. This is an interesting talk. Are there libraries that do this at compile time through static analysis instead of at runtime?
Yeah, so they wouldn't be libraries, they would be checkers. And I suppose one language that has a library that performs that is C++ with the boost library. And that takes care of it all at compile time. So in a sense, that's doing the same as what F# has. But we interestingly found a few problems people had with using C++, that in a sense it's too big. The boost library is too big, and this is possibly why teams like to roll their own library rather than use some of these very accomplished but rather large and quirky libraries. But it's that the example you mentioned is a kind of a fringe case. I've been looking at more of these lightweight ones, and they exist and they're really good, but they don't necessarily guarantee completeness. They just try and propagate unit information from annotated base libraries as much as possible, and they're very good. So it's depending on what your needs are. Do you need 100% correctness? Or are you happy just to try and remove the obvious problems? In which case, that's the way a lot of research is going in this field.
Okay, thank you again. And I think we have to move to our next presentation of this session. And this will be improving the effectiveness of traceability link recovery using hierarchical Bayesian networks. And our speaker is Kevin Moran.
Okay, thank you very much for the introduction, Andrea. I'm really excited to be here today to be able to discuss our work on improving the effectiveness of traceability link recovery using hierarchical Bayesian networks. So this was a joint work that was completed with researchers at the College of William and Mary, as well as with Cisco's Advanced Security Research Group. So before I jump into our approach, I want to talk a little bit about the problem that motivates this in practice. So we've seen a lot about what traceability is today, and the problem that we're focusing on in particular is being able to follow the life cycle of requirement in both a forward and a backward direction by linking these two source and test code artifacts. Now, this has been shown to be a very intellectually intensive task in practice. So there has been a wealth of research that has investigated automated techniques in order to assist developers and analysts in completing this task. Now, many of these techniques use textual similarity metrics in order to equate documents and suggest ones that may be linked together. So in our research, we found that there are three main limitations of these current automated techniques that we set out to overcome with our approach. So the first of these is a limited view or measurement of artifact similarity. So a lot of these different IR techniques like SVM, LDA, LSI, they capture some aspect of the similarity between artifacts, but past work has also shown that this can be orthogonal. So there's some differences in the types of information that these different approaches capture. In addition to this, it's difficult to know which of these approaches you should use in practice in order to get the best performance if you have a brand new data set where there's no existing trace links. Second, a lot of automated traceability techniques really don't have an ability to effectively capture and leverage developer feedback in order to improve the links in their system. And finally, third, there's a relatively limited view between different types of interactions between artifacts. So if we want to be able to try to capture some of these transitive properties, these transitive relationships between links, and I'll explain this further in a little bit. So how can we overcome these limitations? So our approach essentially tries to take a probabilistic view of this traceability problem. So we cast this as trying to estimate the probability that a trace link exists as it's influenced by several different factors. So in order to do this, we have proposed something called a hierarchical Bayesian network. So this is a mathematical representation of the model in something called plate notation. But for the purposes of this talk, I'm going to simplify things a little bit and talk about this, inform something called a trace link prior. And from this, we're able to derive a probability that a given trace link exists between pairs of artifacts. And this model is computed on a per link basis, so between individual pairs of artifacts. And it's also worth noting that the first stage of our model, you can kind of think of as a base case. So this is the one that's always computed, and then stage 2 and stage 3 are essentially added on top of this in order to further improve or provide flexibility to the model. Okay, so let's go through each of these stages. So for the first stage, we want to unify these textual similarity measures. We want to try to capture these differences, these slight differences in orthogonality in order to improve the overall performance. So in order to do this, we essentially run a number of different IR techniques between these artifact pairs. And we normalize these, and from this normalization, we're actually able to calculate a beta distribution. And this distribution will be the first piece of information that we use to inform that trace link prior. So in the second stage, we want to try to incorporate developer feedback. So to do this, we have developers observe certain links. They give a score between 0 and 1 as to whether or not that link exists, with 1 being that that link almost assuredly exists. And from this, we're able to estimate a Bernoulli distribution. And we're able to use this Bernoulli distribution to, in essence, slightly modify that first beta distribution that we estimated. And in this way, we're able to have these developers essentially further refine these different links. So finally, we also want to leverage the transitive information that could exist. So for example, if we have 2 source artifacts, 2 requirements, and 1 target artifact, which is a piece of source code, if we know that S1 and T1 and S1 and S2 are related above some threshold T, then we know implicitly that this is going to influence the potential of the relationship between S2 and T1. So in order to capture this information, we're actually able to estimate a beta mixture model, and from this derive a mediated normal distribution, which can again basically influence that first stage beta distribution that we calculated to begin. So we can put all 3 of these stages together in order to get the 4th stage, or the final stage of our model. And then we need to actually infer the overall posterior probability distribution. Because of the complexity of our model, it can't be calculated analytically. So we have 3 different estimation techniques that we use. The first is called maximum a posteriori, or MAP. The second is a Monte Carlo technique called no U-turn sampling. And the third is a machine learning technique called variational inference. So we conducted a wide-ranging empirical evaluation of this approach, and I'm going to give a brief overview in this talk, and I'm happy to answer more questions. So we had 5 research questions, and the first 4 research questions essentially dealt with asking, okay, how effective is each consecutive stage of the model? And then we had a final research question where we wanted to see, okay, would developers actually find something like this useful in practice if we deployed this? So for research question 1 through research question 4, we studied 8 data sets. We had 2 that we used to tune some parameters of our model, and we had 6 that we used to actually test things. And the libEST project is actually a project where we derive the ground truth, and this is one that comes from our partners at Cisco Systems. And we also used a number of different IR and ML techniques that we use to inform Comet's hierarchical Bayesian network, as well as serve as baselines for our approach. For research question 5, we had 6 developers from Cisco who were contributing to that libEST project. We gave them a 15-minute presentation about a Jenkins plugin that actually implements the first stage of Comet's model. Then we have them use this Jenkins plugin and answer some user experience questionnaires. So this is an example of what the Jenkins plugin looks like in practice. So they can use it to view the similarity between different types of artifacts, as well as provide some feedback. So I'm going to briefly go over the results that we got for the first stage and the final stage of our model. So what I want to highlight here is that the first stage of our model performs about as well or better than the median of the baseline IR techniques. Essentially what this means is that you could take our model on an unseen data set, apply it, and it would perform about as well as the average baseline IR technique. However, for the last stage of our model, we start to see the performance approaching the best baseline IR techniques. So if you're able to use the full version of our model, we think that you'd probably see precision that is approaching the best of the baseline IR techniques. So what we saw for the developer study was that developers really did like using this tool, and we got some strong qualitative feedback from this. So developers found that the tool was easy to use. They felt that the links were generally pretty accurate for the project they were working on, and this was really encouraging for the potential practical applicability. So that's all I have for today, and I'm happy to answer any quick questions, and I'll stick around in Slack later on as well to discuss things. The study and code data are also available at that URL. Thank you very much.
Thank you very much, Kevin. We have a question from Jane. Great talk. Please explain why you ask developers to give feedback on a scale 0 to 1 rather than binary. And how often do they use mid-levels of the scale?
Yeah, that's a great question. So this was partly due to the constraints of the model that we're using. So we wanted to be able to have some scale between 0 and 1, so we could estimate the type of distribution that we wanted in order to fit within the constraints of our model. So what we actually did in the Jenkins plugin is we gave them 4 different options. We said basically strongly agree, disagree, or strongly disagree. And we basically mapped those to one of those different values between 0 and 1. So this way it eliminated some of the complexity and it made it so that developers could think about these things in a bit more simple terms. So we did think about that part of the user experience when we actually went to deploy this with developers at Cisco.
Thank you. We have time for one extra question. How much flexibility for adjusting the model, example, set different priors or dependencies, does your approach allow? What interface should the user use for that?
Good question. So in essence, what we really wanted to do was abstract a lot of the model intricacies away from the person who would be using this. So basically, our intention was if we can kind of fine tune and perform research on the model where we can get it to perform in an optimal way, then the users won't even have to deal with that complexity. So they won't have to think about what prior should I use to work well on this data set. As far as flexibility, most of the derived distributions that we have are based on the theory of conjugate priors. So there is some flexibility in kind of moving these around, but you'd have to make sure that the priors that you're estimating are going to be able to influence one another in the correct way. So what we came up with was essentially our kind of first shot at this.
Okay, thank you. I think we have to conclude and thank all the speakers of this session. Just to remind everyone that all the presenters will be available in the lobby's video chat during the 3rd hour. Also, don't forget to visit the SRC posters, the demos, attend the Ask Me Anything from Bashar Nusseibeh and stop by the Facebook booth. Thank you very much and enjoy the rest of your conference. We also have another session late after this one. Thank you.
welcome to session A12 on testing. My name is Sasha Misailovic. I'm from the University of Illinois at Urbana-Champaign. We'll have an assortment of interesting talks in this session. Please leave your questions on the Clouder in the Slido box. For every talk, we'll have the presenter speak, and then we'll have time for several questions. So our first talk is a technical talk, and it's on practical fault detection in Puppet programs, and it will be presented by Theodoris Sotiropoulos from the Athens University of Economics and Business. Theodoris, you can go.
Thank you. I'm Theodoris, and I'm from Athens University of Economics and Business. I'm going to present our work for detecting faults in Puppet programs. This joint work with Dimitris Mitropoulos and Professor Diomidis Pinellis. To begin with, Puppet is one of the most popular configuration management tools and is widely used by many organizations. It enables administrators to set up their computer systems in a declarative manner through its domain-specific language. Here, you can see a simple Puppet program that boots the Apache service. This program consists of 3 resources. A resource in Puppet is a unit that abstracts the state of a resource in the system. Here, for example, we have a configuration file named etc apache2 apache2.conf. We specify its contents, permissions, and ownership. The Puppet code is organized in files called manifests, and Puppet collects those files and translates them into a single catalog, which is the input of the Puppet execution engine. In this example, Puppet is free to schedule resources in any execution order. So depending on the execution plan followed by Puppet, we might get a crash, or we might get a subtle error, for example, when Puppet starts the service before specifying the contents of its configuration file. To fix those ordering violations, developers need to explicitly specify the ordering constraints between dependent resources. Now, another important feature of Puppet is called notification. A Puppet resource can notify another resource whenever the former is updated. Notifications are very useful for services. So if, for example, when a configuration file is updated, the services that depend on that file need to restart in order to get the updated configuration. Failing to do so can seriously degrade the reliability of service. For example, a missing notifier in the GitHub Puppet code base led to a chain of failures that caused a 42-minute downtime. Again, to fix these problems, developers need to explicitly provide the notify parameter in the specification of resources. Note here that the notify also implies happens before relations between resources. So in this example, the packets of the file resources are executed before the service resource. To detect missing notifiers and ordering violations in Puppet programs, we propose a dynamic analysis which is shown in the diagram. Let's briefly discuss each step in detail. The input of our approach is a Puppet manifest that we want to analyze. The executor applies the given Puppet manifest in the system, monitors its execution, and collects its system called trace. The executor also stores the compiled catalog of the initial Puppet manifest for later use, as we will discuss later. On the right, you can see a faulty Puppet program that contains a missing notifier from the file resource to the service resource. The next step of our approach is the analysis of the trace produced by the first step. The first step of the analyzer is to translate the trace into a formal model that allows us to compute the interactions of every Puppet resource with the file system. To do so, we provide a semantics for that formal model, and we split the trace into blocks corresponding to the execution boundaries of every Puppet resource. Here, you can see a small fragment of the system called trace stemming from the execution of our example program. To get the idea, the high-level idea of how the analyzer works, it first identifies the points, for example, where the execution of the file resource begins and ends. Since the execution of a Puppet resource does not interleave with the execution of another resource, we presume that the system calls between those points stem from the execution of the file resource. We do the same for the service resource, and through our semantics, we know how and where its file is accessed. So for example, the configuration file of the Apache service is produced by the file resource while it is consumed by the service resource. Having computed those file access, the analyzer now infers relationships between Puppet resources. We have two kinds of relationships. We have ordering relationships and notification relationships. Back to our example, by exploiting the file X on the top and the inference rules on the left, the analyzer infers two relationships. The first relationship says that the execution of the file resource precedes the execution of the service resource, while the second relationship states that the file resource notifies the service resource. The final step of our approach is fault detection. The first step of the fault detector is to build the dependency graph of the given Puppet program by examining the compiled catalog produced by the first step of our approach. Note here that this dependency graph contains all ordering and notification relationships that actually appear in the program. That is, they have been explicitly declared by the developers. Here, for example, is the the dependency graph of our example program. Now, the second step of the fault detector is to verify whether its relationship inferred previously by the trace analyzer holds with regards to the dependency graph. Back to our example, through an algorithm which is described in detail in our paper that examines the reachability relation between the nodes in the dependency graph, the fault detector knows that the first relationship holds while the second one does not. So it reports missing notifier for the file resource to the service resource. Let's proceed to the evaluation. We analyzed 354 Puppet modules taken from Forge, which is the official repository for uploading Puppet modules. We applied each module in a fresh Debian environment by spawning Docker containers. Our approach detected 92 previously unknown issues in 33 Puppet modules, and the majority of them have been fixed by the developers. We also categorized the detected faults in various patterns related to ordering violations and missing notifiers. And let's briefly discuss one fault pattern, which is one of my personal favorites, and it's related to missing notifiers from log files to services. So we have a log file, so we have a service. When the service starts, it opens this log file and creates a file descriptor that points to the underlying log file. Now consider that this file is removed from the file system and we run Puppet again to recreate. So the file path of this log file points to a new file. However, the service still has a file descriptor that points to the initial file. The issue here is that this file has become an orphan. That means that it cannot be accessed through a file path. So we have data loss here. The service needs to restart to open the freshly created log file. Regarding performance, for collecting trace, our approach slowed down Puppet by almost a factor of 2. The trace analysis and fault detection take 2 seconds on average, and the time spent on trace analysis is linear to the size of traces. To conclude, we introduced an effective and practical approach for detecting ordering violations and missing notifiers in Puppet programs. We do believe that our approach could be part of the testing process for Puppet programs due to efficiency and effectiveness. For everyone who wants to take a look, this the repo of the tool used to analyze the Puppet module and the artifact used to obtain the experimental results. Thank you for listening.
Thank you very much, Theodoris. So let's see if we have any questions. Before anyone types their question in, let me start with one question. So on the last slide, you showed the scaling seems to be linear. Is that a trend that you expect even when the trace size goes larger, or is there a point where it will break?
Yes, when we inspect larger traces, the trend still holds because actually the analysis of trace is just a linear pass of the examined trace. So yes.
Okay.
So you can see here that our approach could analyze gigabyte of traces in a few seconds.
Okay, great. Another quick question, can this approach work even in the case when you don't have the access to the full dependency graph?
Actually, we always have the full dependency graph because this reflects, this graph is computed by examining the compile catalog of the given manifest. And this file, this catalog is produced by the Puppet and reflects before the execution of the program and reflects reflects the execution plan that is going to be followed by Puppet. So okay. Yeah, we have the full dependency graph.
All right, thank you very much. Now it's time to move to the next talk. So the next talk is a journal first paper. It is on empirical assessment of multimorphic testing, and it will be presented by Paul Temple from the University of Namur. Paul, it's your time. Paul, I think you're muted.
Sorry, thank you. Thank you for the introduction. I will present a new testing framework that we have developed with Mathieu Hacher and Jean-Marc Gézéquel from the University of Rennes in France, that we have called the multimorphic testing framework, that is used to assess the relative quality of test suites to reveal the different behaviors of software systems, of software variants. So you know that recent modern software are quite complex and they need extensive testing. And this testing phase is also quite expensive in computation time and resources. And especially when you try to benchmark different techniques, you may wonder in the end if all the different tests that you have run are really worth it. And this is what the multimorphic testing framework is about. So you start in this figure at the top left, on the top left side with a software system that is configured or that uses a specific implementation of a technique that you will derive into different variants that you call morphs in this framework. And so you derive this software system by changing the configuration or by changing the technique that is used in this implementation. And so you end up with a set of morphs that probably behave quite, a little bit differently one to another. Based on these sets, you can execute them on the different test cases that you have on the left of this figure in order to measure a property of interest that you have defined previously, and you report these measures into the cell of a performance matrix. Sorry, that is at the center of this figure. Then, based on all those different measures, you can use, again, a previously defined score in order to, in the end, rank the different test cases. And based on these ranks, you can optimize your test suites as you wish. So there are three main phases in this framework. The first one is called multimorphing. It can leverage traditional derivation technique from the software product line world. So to change the configuration of a software system, or to, if you want, you can also, as I said before, change the technique or the implementation of a specific algorithm that is used in the software. The second phase is only about measuring the property of interest, so nothing new here. And what's interesting is the third part, which is defining the score and use it to rank the different test cases. So we spend quite some effort in this paper to provide the different suitable properties that such a score should provide. And we also propose a score, a measure that we have called the dispersion score. Okay, so this was the presentation of the framework. We also, in the paper, have ran some evaluations on different use cases, three of them. And one of them was the Microsoft Common Object in Context competition, so the MS COCO competition, which is run every year to benchmark different object recognition techniques. And in the year 2017, 52 competitors ran this competition. And as you can see, there was 160,000 different images that were used. Among them, 40,000 were used to test and rank the competitors. So you may wonder if you really need all those 40,000 different images. And so we applied the multimorphic testing framework on this set of images, and we managed to reduce it to 17,000 images, different images. We rank again the competitors with this reduced set of images, and we compared our ranking with the original one from the competition. Turns out with this reduced set of 17,000 images, we retrieve almost the same ranking with only few permutations in the ranking that appear from time to time, like 5 times or something like that. So it suggests that we only need these 17,000 different images instead of the original set of 40,000 images to rank properly the competitors. So it's quite promising as a result. And as I said in the paper, we also made an evaluation on 2 other different use cases. And again, the results are quite interesting and promising. So again, feel free to read this paper. If you have any question about this, don't hesitate to contact us, one of us. And also, we are always looking for new collaborations or any candidates. So feel free to contact us. And at the bottom of this slide, there are 2 links to the original paper in the Transaction on Software Engineering Journal and a preprint version on AL. Thank you for listening.
All right, thank you very much, Paul. Let's see, do we have any questions on Slido? Seems like nothing yet. So just a very quick question. How do you envision developers incorporating that in their in their workflow?
Yeah, so I guess that you need somehow to measure all the the different performance of the different morphs for the different test cases in order to run this framework. Then once you have done that once, you can then try to optimize your test fits. And if you're in a DevOps way of developing, maybe you can leverage this framework to reduce the testing activity.
Okay, very well. Time. Thank you. Thank you very much. So now time to move on to the next talk. Our next talk is going to be a demo talk. It is by Matthias Martinez from the University Polytechnique House de France. And he will present RTJ, a Java framework for detecting and refactoring rotten green test cases. So green test cases can rot. So that's funny. All right.
Hello, everyone. My name is Matthias Martinez from University Polytechnique de France, and I would like to present RTJ, a Java framework for detecting and refactoring rotten green test cases. It's a tool that I have made with the colleagues from University of Lille, INRIA Lille, and the Technologie Supérieure de Montréal. So first, I would like to define what is a rotten green test. So rotten green test is a passing test case, a green test, which has at least one assertion that it was not executed. So rotten green tests are bad because give developers false confidence. So in the paper, we present 4 kinds of rotten green tests. Here I will present only one example of the category context-dependent test. In this case, is a test case that is passing, but it has some assertions that are not executed. For instance, in this case, we have an assertion that is inside one if. If in this case, the variable x has a value greater than 0, the assertion is not executed. So the rotten green tests were studied in the context of Fire language. In this paper, we present a tool that is able to detect rotten green tests in Java. So the tool is available on GitHub, so you can download it. So how it works, basically it's apply first static analysis for detecting different code elements, for instance, assertions, helper, etc. And then apply dynamic analysis to determine the execution of those elements. So to evaluate the tool, we have select 67 popular open source Java projects from Java. So the condition was that the project used JUnit 4, has Java as main languages, also that it's used Maven as a dependency management system, etc. So in total, we found more than 400 rotten green tests in 26 projects. That means that more or less 1 out of 3 projects has at least one rotten green test case. So as conclusion, so in this paper, we present a tool for detecting green rotten tests for Java. The tool is open source. It can be used by researchers for defining new categories of rotten green tests. For extending the tool, it has different extension points. And also for software practitioners, that they can analyze their projects to know whether they have rotten green test cases. That's it. If you have any question, I will be available. Thanks.
Thank you very much. In the interest of time, we need to move on to the next talk. So the next talk is a new idea talk on a container-based infrastructure for fuzzy-driven root causing a container-based infrastructure for fuzzy-driven root causing of flaky tests, and to be presented by Valerio Terragini from the University of della Svizzera Italiana. Valerio.
Okay, one moment. Okay, so hello everyone. My name is Valerio Terragni. I'm a postdoc of USI, and this is a joint work with Pasquale Salza from the University of Zurich and Filomena Ferrucci from the University of Salerno. So the flaky tests are tests that pass or or fail non-deterministically when executed on the same program version. Flaky tests are very harmful because test failure do not always indicate bugs in the code. And every time a flakiness occurs, the developers, they have to reason whether is the problem the production code or is the problem in the test itself. In other words, they need to find the root cause of a flaky test. Existing root cause analysis for a test flakiness rely on execution logs obtained with code instrumentation. These approaches have three issues. First, they need to decide what to instrument, but this depends on the type of flakiness that is something unknown in advance. Of course, instrumenting every line of code is unfeasible. Second, the use of instrumentation may prevent the manifestation of flaky test failures. Third, they passively explore the non-deterministic space by re-executing the test many times, hoping that a flakiness will occur. Our new idea is a methodology for root-causing flaky tests that does not rely on any form of instrumentation and actively explores the non-deterministic space. Our idea is to execute a flaky test on different execution clusters, and each cluster explores a specific non-deterministic dimension that characterizes the type of flakiness. For instance, a concurrency, networking, or I/O. Based on how many times the test fails in each cluster, we can identify the most likely root cause. In this case, the flakiness happened only in the network cluster. Thus, we can infer with high confidence that the non-determinism of the network is the most likely root cause. More specifically, we envision a dedicated execution cluster for the most common types of test flakiness. And we have that each execution cluster has associated a fuzzy loader that generates dummy operation that perturbs the execution of the test, and also a container, a configuration, which specify the available resources. In this case, as an example for the multi-thread cluster, we have the fuzzy loader, which will execute dummy operation on multiple threads, while the container configuration specifies the number of available cores. Every time a test executes on a cluster, we change the load of the fuzzy loader and the container configuration. This will actively explore the non-deterministic dimension associated to the cluster. After we execute the test, we can compare the failure rate with a baseline cluster that executes the test without perturbing the execution environment. We select as the root cause the cluster that has a failure rate that differs the most with respect to the failure rate of the baseline cluster. In this case, is the I/O cluster. Thank you for your attention.
Thank you very much. We have time for a question. There is one question. So would this approach be envisioned to work, say, for future heterogeneous systems, like consist of CPUs, GPUs, FPGAs?
Oh, this is a very good question. So for a heterogeneous system, we might think about other cluster that might perturb the GPU, but yeah, it's a very good question. So we might think to also consider a GPU cluster.
Okay, thank you. There are more questions, but we'll have to move on. The speaker will remain online after the session, so you can ask then. So our next talk is another journal first Oh, my bad. Our next paper is another technical paper, a technical session paper. It's learning from, understanding, and supporting DevOps artifacts for Docker. And it will be presented by Jordan Henkel from the University of Wisconsin-Madison. Jordan,
okay. Hi, ICSI 2020. I'm Jordan Hinkle from the University of Wisconsin-Madison. I'm here to talk to you today about some work I did in learning from DevOps artifacts, in particular Docker files. And I did this work last summer at Microsoft Research Redmond with my colleagues Chris Bird and Shubhendu Lahiri and my advisor, Tom Reps. So I want to kick things off by just talking about DevOps in general. What is DevOps? To me, it's just an ecosystem of a bunch of different DevOps tools. It's also a blend of the words development and operations. And these tools, they exist to help developers meet operational goals like continuous integration and testing and managing containers. Maybe you've heard of some of these tools before, maybe not. But regardless, there are many, many tools in this DevOps ecosystem. And something interesting about these tools is that many of them take an input artifact of some sort. So for Docker, that's a Docker file. For Travis, it's a Travis file, and so on. And these input artifacts to these tools, they're structured, they're complex. They usually live in a repository alongside the code. They're maintained, they evolve, all that good stuff. I'm going to call those DevOps artifacts. So hopefully this helps us set us up on the right foot. When I talk about DevOps artifacts, I'm talking about things like Docker files. And in general, we analyzed something like 900,000 repositories. About a quarter had some form of DevOps artifact. But for this talk and for the paper, we focus specifically on Docker and Docker files. So the things I show and talk about are really going to be in the context of Docker and Docker files, but should apply more generally to any of these kinds of DevOps artifacts. So what's the problem? Well, we have really great support for traditional programming languages, and we have really great support in our development environments to catch mistakes, to find errors and issues before they really occur, before we even compile and run the code. But when it comes to DevOps artifacts, there's nowhere near the same level of support. Particularly for a tool like Docker and Docker files, there's regex-based syntax highlighting, there's some external linters you can invoke, but there's really not much in the way of good support in the IDE. So you might ask, why don't we do more? Why don't we have good support for DevOps artifacts? And I think that's a good question. And I think the answer is we could. We could spend a lot of time and effort into making good tools for DevOps artifacts like Docker files. But DevOps tools, they evolve really quickly, right? This is still a fairly recent kind of paradigm or area. There are a lot of different tools in this ecosystem. There are new ones each year. And as the community moves from one to the next very rapidly, it creates this kind of high risk, low reward situation. You could invest a lot of time and energy into building good support for any given artifact type, like a Docker file or a Jenkins file. But what if next year there's a new, better tool in a different format and you kind of have wasted your effort? So we had some goals here. We were inspired by the growing interest in learning rules from data. So in this case, it was learning rules from just regular programming languages, regular code, to support simple linting and AST-based static checkers. That's really cool. And we thought, well, this is great. What if we could just do the same thing for DevOps artifacts like Docker files? What if we could take a bunch of Docker files on GitHub and learn rules from them, and then we could kind of get, for free or with very minimal effort, better semantics-aware support that you could plug into a development environment without having to expend a lot of effort and kind of turn this high-risk situation into a more low-risk situation to get a lot of what we want in an automated fashion. Of course, this sounds nice, and we do make progress towards this, but there are some challenges, the first of which is the fact that these DevOps artifacts like Docker files have a lot of nested languages. And I'll go more into depth on this challenge in the coming slides, but this is a particularly thorny issue that we have to deal with. It's not like code where, there's Python and yeah, it's Python. It's more like there's several layers of languages that you have to work with and you have to represent if you want to make progress in this area. The second issue is that if you're going to do static checking, you're going to need an analysis engine, a rule encoding, all of that kind of good stuff. I would encourage you to check out our paper for details on that. We have those good things. We use tree association rules as our rule encoding. We also are able to mine automatically tree association rules to feed into that checking engine. But that's not what I'm going to focus on for the rest of this talk. Instead, I'm going to focus on this challenge of nested languages, because I think this is something a little bit unique to DevOps artifacts and something quite interesting to look at further. But before I go there completely, I'm going to just look at a single Docker file to provide some intuition. So on my screen right now, this is a Docker file. You can think of it as just a sequence of directives. It's a sequence of steps, and these steps, as you follow them, they're like setup instructions is how I would think of them. They're each an individual thing you need to do to get a container or your image up and running. Think of it like a README, the installation instructions almost for a project. That's what you're seeing in the Docker file. I'd also try to maybe draw an analogy to makefiles. Makefiles, you have targets, and then within the targets, you do different things. This is quite similar to Docker files. You see that run statement in the Docker file. Well, there you're doing some bash to install packages and set stuff up further. And then maybe in the bash, you invoke different commands like grep or a Python interpreter. And then within that, you have more sublanguages. So hopefully you can kind of get an intuition here that there's a lot of nested languages going on. There's a top level, like a makefile. Just like targets, we have kind of nested places where we do specific setup. That could be in a different language, primarily bash, and so on and so forth. And the mistakes that are occurring here, they're often in the subtle differences between how you're using bash interactively in the command line and how you're using it within something like a Docker file, or really any of these DevOps artifacts. There's subtle differences in the usage of these tools. You know, on the command line, I might sudo apt-get install some packages, but in the Docker file, I might not be doing that. I might instead just need to apt-get install with a non-interactive flag to make sure the build doesn't hang. So these subtle differences are the source of a lot of, I guess you could call them code smells or issues with DevOps artifacts like Docker files. So how do we deal with this nesting? What do we do? Well, we do the pretty direct thing. We invoke a Docker file parser, and we get a tree that represents the Docker file. And this is all right, this is fine, but it's pretty shallow. And wrapped up in that unknown node, there's a bunch of leaf nodes in this tree that are just big string literals. And in those string literals, at this level, it's primarily bash. We could parse within those to get more structure. If we don't do that, we'll have to do some sort of regex-based matching or fuzzy matching, and that's sad. And as part of phase parsing, kind of our core idea here, we do the direct thing and we do parse within. So we have this leaf node, it has some bash in it, we invoke a bash parser, and then oddly enough, we've made stuff worse because now there are two leaf nodes. Again, they're kind of these big string literals. They have further structure we could discover. Later, I'll call them effectively uninterpretable, right? So they exist. We could do fuzzy matching, but that's kind of sad. So we want to do more. We want to do something structural, but we don't have the languages. We don't have another parser. You know, it's if only sort of thing. If only we had more parsers and more grammars for these sublanguages, we could expand the tree in a structured way further. And that's where things get interesting. So if you look at this bash within this Docker file and you look at these effectively uninterpretable leaves, if you wanted to parse these, now you need a bunch of different parsers because there's apt-get, which has its own options languages, and then there's get, which has its own set of commands and flags, and curl and wget, and so on and so forth. There are a bunch of these different utilities with different kind of specs and options formats. So we needed to find a way to take care of a lot of these. And to do that, we had a parser generator that we built. And this parser generator is clever in that it takes an input artifact that looks a lot like the embedded help you might find in apt-get or get. You know, a lot of these commands you can do --help, or you can look at the man page. We take as input to this parser generator something that looks like that. And of course, we don't take just the embedded help directly because it's a natural language and that's difficult to parse and work with. But by taking that embedded help, we can generate a bunch more parsers for these third level languages. And we do that for the 50 most popular bash commands used within Docker files. And if you put that all together, what you get is you get like a really good abstract syntax tree for Docker files. At phase 1, you have this very shallow tree that isn't super useful. At phase 2, you can parse the embedded bash and actually make some things worse, funny enough. But as you go all the way down, you just get this really good, rich, structured representation of Docker files that'll enable interesting things like pattern mining and static checking in a structural way. So quickly, some experiments. Phase parsing does what you'd think it would do. At the first phase, about a fifth of the leaf nodes are uninterpretable. When we add the bash parser in, things actually get worse. We go to a third of the leaf nodes that are uninterpretable. But when we add these 50 generated parsers that we created, we get down to just around 4% of nodes that remain uninterpretable after that phase. So that's really great because we can see more, which means we can do more. And then if we look at rule mining and checking, we do automated rule mining using kind of frequent subtree mining and some slight modifications to that. We get about 2/3 of a set of ground truth rules that we manually mined recovered automatically. We also find 16 new rules, the details of which are in the paper. And then when it comes to checking, we find that there's actually a 33% mean violation rate for this big corpus of Docker files we collected from GitHub. And we actually find that's 5 times worse when we compare it to files written by experts. So with that, I just want to say thanks. You should check out our paper. We also have a corresponding data showcase paper that you could check out with the data sets and some details and an artifact on GitHub. And I'm happy to take questions.
Thank you very much, Jordan. pretty interesting. We have time for 1 or 2 questions. Let's see if there is anything on the slide. Still nothing. Okay, then let me ask a question. And can you elaborate a little bit about what static analysis do you use, about the second part that you skipped in the talk?
Yeah. So we do a simple, just kind of, once we get these good abstract syntax trees, we can just do tree association rule-based checking, where we say, if I see a certain subtree, now that we have good representation, I expect to see this other subtree either before or as a descendant or after that subtree. So that's what we end up doing for this static analysis, is just a simple this then that style of checking, where we have these subtrees that we match against the corpus we're analyzing.
All right. Okay. Thank you very much.
Thank you.
It's time to move to the next talk. So our next presenter is Gemma Catolino from the Delft University of Technology. And this is a journal first paper. It's on improving change prediction models with code smell related information. Gemma, you can start. You're muted.
You see my presentation, right?
Yes.
Okay, so hi everyone. I'm Gemma Catolino from Delft University of Technology, and today I'm going to present our journal first paper that has the goal to improve change prediction models with code smell related information. So there is some problem. I have problem with, okay. I don't know why I cannot change my slide. Sorry. Live problem.
It's usually how it happens.
Yeah, I really don't know the problem. Okay, let's do it this way. Yeah, I try to do again. Sorry. Yes. Okay. Okay, yes. Perfect. So during the evolution of software, change is unavoidable. So knowing in advance the code elements that exhibit a higher change prone is crucial for developers. And in the past, research community spent a lot of effort in order to present paper, especially in the context of change prediction. And in particular, also in our previous studies, we explored how developer-related factor can be a useful source of information to predict classes more likely to be changed in the future. In particular, we relied on 3 models previously used in the context of bug prediction that explore how developer apply change in the code, and we use in the context of change prediction model. What we discovered was that model using bug prediction work well also in change prediction context, that the performance increased compared to the baseline, and we notice also high complementarity between the metrics. But according to a paper of Com et al., we know that the presence of code smell can impact the change and fault proneness of a code component. For this reason, in this journal, we conjecture that the addition of a measure of intensity of code smell could improve the performance of change prediction models. In particular, in order to detect the code smell intensity, there is this tool called J-code odor, and in particular, this tool measuring the severity of code smells, and in particular for 6 code smells, and based on the value on some structural metrics, give the value of the intensity from 1 to 10. In the context of our papers, we relied on 2 types of datasets. One dataset proposed by Uresco and Madeschi, and one dataset of Palombe et al. In particular, this dataset consisted of 41 releases of 14 projects, and we joined this data set together, and these data sets contain already information about intensity index, anti-pattern metrics proposed by Tab et al., structural metrics, and developer-related factors, so based on the 3 models that I explained above. We additionally computed information related to change-prone baseline models, and so we had our independent variables. As for the dependent variables, we additionally computed change-prone classes using change distiller tool. In order to construct our model, we constructed 5 different machine learning models. In particular, the model based on structural and process metrics acted as a change prediction model baseline. And as for developer metrics, we have the 3 prediction models that I explained above. For each of them, we added intensity index and anti-pattern metrics. And in particular, let me provide you an example. So we have our model that included only structural metrics plus the intensity, and finally, structural metrics plus anti-pattern metrics. We run our model using logistic regression machine learning technique and use tenfold cross-validation as a validation strategy. And as first results, we have that also in this case, models that consider a developer-related factor together with intensity worked well compared to the other baseline, and also compared to the model that includes anti-pattern metrics. But we notice also high complementarity, and for this reason, we put all these factors together. We apply a feature selection method, and we rerun the model, and we try to compare the results. So as a result, we have, as I said before, that developer-related models together with intensity metrics work better than the baseline, but also that combined model that includes all the factors boosts the performance compared to the other one. As a future work, we plan to, of course, put this approach inside the tool in order to prioritize maintenance intervention. And that's it. If there is any question, I'm happy to answer.
This is great. Thank you very much. We have a question on the slide too. So what is the granularity of your change prediction? Is it file, class, method?
Classes, granularity.
All right. Okay. Thank you. Let's see if. All right. Let me then ask one question myself. So, what is the sensitivity of your results to the choice of the metrics that you used?
What is, sorry?
The sensitivity of the results to the choice of the metrics and their thresholds, I guess.
I think I don't catch the point. What do you mean for sensitivity?
So if somebody goes and changes one metric for another one, or changes the threshold of that metric, how much would the results change, or your findings?
Yes, of course. I mean, also when we apply feature selection technique, is also because in a way maybe there are some metrics that in a way or another can explain the phenomenon in the same way. So for example, several structural metrics during the feature selection technique were removed from the set. But of course, there are especially metrics related to developer-related factor that it seems that can catch better the phenomenon compared to the structural metrics.
All right. Okay. thank you very much. Now it's time to move on to the last presentation this session. And this one will be a recorded talk. So it is another short demo paper presentation on SMRL, a metamorphic security testing tool for web systems.
Tools that automate security testing of web systems by applying metamorphic testing. SMERT enables engineers to specify metamorphic relations that capture security properties of web systems. The SMERT compiler automatically transforms metamorphic relations into Java code. SMERT includes a web crawler that simulates user interacting with the system. The data collected by the crawler is used to generate source input. Then the SMERT framework runs metamorphic relations against the web system under test. I introduced the idea behind our running example. The administrator of a system can access the feature-based settings through the GUI. User 1 cannot access the feature through the GUI, but user 1 can still try to access it using direct requests. A different page should be shown. What we want to do is to generate a follow-up input where we access the same URLs of admin with another user. Now we describe this metamorphic relation in the SMERT language. The source input are the sequences interactions with the web system recorded by a crawler. This metamorphic relation iterates over on the interactions recorded. And it says that if a follow-up user, in this case user, is not a supervisor of the user who performed the recorded interaction, and it cannot read the same URL from its web interface, then a follow-up input that performs the same interaction but with the follow-up user should not lead to the same visualized page. A Java file is automatically generated for each metamorphic relation. To collect source input, we run our crawling framework. This is an example of crawled data. Now we run the metamorphic relation. Before running the test, we provide configuration parameters. This is a portion of the source input files collected for Jenkins. We run the test. There is one failure. The user tools, a normal user can start an agent in Jenkins. This is a vulnerability of Jenkins, and SMERT has just detected this vulnerability. Thank you for your attention.
All right, thank you all. So this concludes our session. Special thanks goes to Efrain and Caroline who made this session possible. And before we leave, just a quick reminder that the presenters of this session will likely be in the lobby during the third hour. For those who register the conference, you can find them on a Clouder. And in the next hour, you can also visit the SRC posters, the demos, or attend the AMA session with Bashar Nusseibeh. And you can also stop by the Facebook booth. So thank you very much and enjoy the rest of the conference.